Let's begin with vectors A and B with these lines of action. This video illustrates how to translate vector A to a concurrent point at the tail of vector B. One cannot simply move vector A from its line of action. In order to move vector A, the moment of A about the concurrent point must be found. To solve for the moment of A about the concurrent point, a radial vector r must be found. The radial vector is any line that goes from the concurrent point to any point along vector A's line of action. It acts as a moment arm for the moment of A about the concurrent point. For simplicity purposes, the radial vector from the concurrent point to the origin of vector A was chosen for this example. Now the radial vector r can be defined, and the moment of vector A about the concurrent point can be calculated. Finding the components of vector r requires information about the geometry of the problem. The cross product may be used to solve for the moment of vector A. Take the two vectors and replace the variables with numbers. Notice the units for the cross product results in Newton meters, which is the correct units for the moment. Now write the determinants. For the I component, shade out the row and column to reveal the I determinant. For the J component, shade out the row and column to reveal the J determinant. Make sure to remember the minus sign on the J determinant. For the K component, shade out the row and column to reveal the K determinant and then add that determinant. Now solve each determinant. The I determinant is 3 times 6 minus 2 times negative 4, which equals 26i. Continue computing the remaining determinants to find the moment of A. Now, vector A's line of action through the concurrent point also includes the moment of A. The moment is commonly shown as a vector with double arrowheads, and it follows the right-hand rule. Fingers curl in the direction of rotation. The thumb points in the moment vector direction. Take a look at R cross A. Point the fingers in the direction of vector R and curl them towards vector A. The thumb points in the direction of the moment vector. Notice again that moment vectors are represented with a double arrowhead. Let's look closely at the cross product to figure out how it works. Vectors are reduced to I, J, and K components. When solving the cross product, begin by solving for the I component, which is parallel to the x-axis. Now sum the moments about Rx. There is no moment for Ax about Rx because Ax is parallel to Rx. Now the perpendicular distance Ry to the line of action of AZ produces a moment about Rx, which is equal to 18 Newton meters. The perpendicular distance Rz to the line of action of AY produces a moment about Rx, which is negative 8 Newton meters. This is subtracted from the previous moment. The resulting moment about Rx is 26 Newton meters. Likewise, the moment about Ry is computed using Ax and Az. These are the only vector components producing about Ry. The moment about RZ is computed using AX and AY. These are the only vector components producing a moment about RZ. The results may be expressed in terms of the moment vector components. Now, vector A's line of action through the concurrent point also includes the moment vector of A.